So now we will discuss about the next topic, which is curvilinear motion. So consider now the continuous motion of a particle along a plane curve. So which is this figure here. So at time t, the particle is at position A. So a particle is moving along this orange path, and at time t, the particle is at position A. And the position of A is specified by this position vector r, which is measured from this convenient fixed origin O. This can be any point here. So r is the position vector of A. And now if the magnitude and direction of r are known at time t, so then the position of the particle is completely specified. Now at time t plus delta t, the particle is at a dash. So now the particle is moving from a to a dash, and during interval delta t, and the a dash is located at this position here, and the position vector of a dash is r plus delta r. So delta r is this vector here, which is from a to a dash. We note, of course, that this combination is a vector addition and not a scalar addition. So as you can see in this figure, that r plus delta r is r plus delta r. So this vector, our position vector, which is the position vector of a dash, is r plus delta r. But this addition is a vector addition, and this r here is a position vector of this a, and then you have delta r, which is again a vector from a to a dash. So when you add these two vectors together using the head to tail rule, so you will get this r plus delta r vector, which is the position vector of a dash. So now we can define a displacement in this curvilinear motion. In the previous topic, we discussed rectilinear motion, where the body was just moving in a straight line, but now the body is moving in a curve. So the displacement of the particle during the time delta t is the vector delta r. So delta r is what we call is the displacement, which represent the vector change of position, and is clearly independent of the choice of the origin. So delta r is nothing to do with the O point. So if you change the O point, so for example, if you change the point to somewhere here, so this is our new O. So again, we will say that the position vector of A, which is r, will be this point here, and the position vector of A dash will be this point here. This will be r plus delta r. Now you can see that r and delta r is changing, but delta r is again from a to a dash, so which is independent of the choice of O. Okay, so if an origin were chosen at some different location, the position r would be changed, but delta r would be unchanged, as you saw here. Now in 1D or in rectilinear motion, it was hard to differentiate between distance and displacement, but in curvilinear motion we can differentiate between displacement and distance. So now the distance in this case you can define is the distance actually traveled by the particle as it moves along the path from A to A dash, so which is when the particle is moving along this orange path. So the the distance will be this line here, and you represent this by delta s, and delta s is measured along this orange path. And thus we distinguish between the vector displacement. So you can see that delta r is the shortest distance between a and a dash, which is a vector, and the scalar, which is delta s, is a scalar quantity. So now you can define velocities here. So the average velocity of a particle between a and a dash is defined as this equation here. So if you divide this delta r, not delta s, delta r, which is displacement, divided by delta t, which is the time taken when the particle moved from a to a dash, which is a vector whose direction is that of delta r. So obviously, this v is a vector and delta r is a vector, and whose magnitude is the magnitude of delta r divided by the delta t. Now, the instantaneous velocity v of the particle is defined as the limiting value of the average velocity as the time interval approaches zero. This is the similar definition as we did in the previous case. So here we can say that velocity, which is a vector, and its instantaneous velocity can be written as like this. So when delta t approaches zero for the average velocity, so this is what we call is the instantaneous velocity. This is the definition of the instantaneous velocity. And we observe that the direction of delta r approaches that to the tangent of the path as delta t approaches zero. And thus the velocity v is always a vector which is tangent to the path. So as you can see on this in this figure here, that at position A, when you calculate the instantaneous velocity, which will be this v here, and v is tangent to this orange path. Similarly, if you want to calculate the velocity at point A dash, again it will be tangent to the path. So this is how you finding out the direction of the instantaneous velocities. Now the instantaneous velocity can be written as dr by dt, and obviously velocity is a vector. R is a vector here, so therefore we are writing these arrows on the top of v and r, and as we did in the previous case, this uh, will be just r dot. So we can say that the velocity is the rate of change of the position vector, or in this case, which is r dot. So this is the change, the rate of change of the position vector is what we call is the velocity. Now, as we already know, we derived in the previous slide that v was equal to limiting value when delta t approaches zero, and that is delta r divided by delta t. Rv is equal to dr by dt, or you can say it is r dot. Now, again, you can also see in these figures. So the velocity of a particle at A is denoted by the tangent vector v, as you can see here in this figure, and the velocity at A dash is represented by this velocity vector, which is v dash. And as you can see here, the velocities are vectors. So if the velocity is changing from A to A dash, so as you can see in this case, uh, even if the magnitude of the velocity is the same, but still you will have you will see some change in velocity, and this is because the velocity is a vector quantity, and clearly there is a vector change in the velocity during the time delta t. When the initial velocity is this one, the final velocity is this one. So this means that there is some change in the velocity, which you can write from this vector here. So this is the final velocity v dash. This was the initial velocity v, and the delta v is the change in velocity. And obviously, this is what we do is a vector addition. Uh, so the change delta v must equal the velocity at a dash. So we can write. So here we can write this equation that v dash, which is again velocity vector, is equal to the velocity vector at a and plus delta v, which is again a vector. So this equation is a vector equation. So this means that you will have to perform this operation using the procedure of vector addition. Now, inspection of the vector diagram show that delta v depend both on the change in magnitude, which is length of v, and the change in direction of v. So even if v and v dash are same in magnitude, you will still have delta v here because it is a vector. Okay, now we can talk about the acceleration. So the definition of acceleration for the curvilinear motion is exactly the same as the definition for the of the acceleration for the rectilinear motion. So first you define the average acceleration here. The average acceleration of a particle between a and a dash. So if the velocity here is v and here is the v dash. So the change in velocity as you calculated here was delta v. So if you divide delta v by the time interval, which is delta t, you will get the average acceleration, which is delta v divided by delta t. And again, which is a vector whose direction is that of delta v. So the acceleration will be in the direction of this delta v. And the magnitude of this average acceleration is the magnitude of delta v divided by the delta t. And similarly, we are also interested to know about the instantaneous acceleration a of a particle is defined is the limiting value of the average acceleration is the time interval approaches zero. So which is this equation here. So when time approaches zero, then what we will have is the delta v divided by delta t, and obviously this is is a vector, velocity is a vector. So the instantaneous acceleration is the limit when delta t tends to zero, and delta v divided by delta t. And by definition, the derivative, so then we can write is that this equation is just this thing here, dv by dt, and obviously a is vector, v is vector, and you can also write this is a v dot, which is the time derivative of the velocity here. Now we can talk about the rectangular coordinate system, which is xy coordinate system, as you can see in this case here. So the system of coordinate is particularly useful for describing motion when where the x and y component of the acceleration are independently generated or determined. Now the resulting curvilinear motion is then obtained by vector combination of x and y component of the position vector, the velocity and the acceleration. So in this case, as you can see in this figure here, that r is a vector of position vector of point A from here to here. And we can see that in xy coordinate system, which is the rectangular coordinate system, this r can be split into two components. One is the x component and one is the y component here. So we can write r, which is a vector, and which can be write is x I plus y j. This I and j are the unit vectors. So I is the unit vector along x, and j is the unit vector along y. So we can write r in this way here. Similarly, you can differentiate this r with respect to time, and you will get the velocities. So if you differentiate this r with respect to velocity, so you will get r dot, which is dr by dt, and you will get x dot, which is a dx by dt, and again this is I, and y dot, which is uh, the dy by dt, and j. Similarly, you can calculate acceleration, which is again v dot, and again acceleration is vector, v is vector, and r double dot, which is again x double dot along I plus y double dot along j. We can also write these vectors. So as you can see in this case here, that the velocity, um, so this equation is then vx I plus vy j, and similarly x double dot is ax I plus ay j. So which you can see in this figure here, that r can be split into x, y. So y along j and x along I. Similarly, the velocity v, which is the velocity instantaneous velocity at a of a particle, and again this can be split into x component, which is vx along I, which is this vx along I, and then vy along j, which you can write like this. And similarly, the acceleration of a particle. So if the acceleration is in this direction here, the total acceleration, it can be split into two components, in x direction and in y direction. So which is, you can see the ax is the x component of acceleration and ay is the y component of this acceleration. Now you can also calculate the magnitude of the velocity from its component, which is vx square plus vy square. So from here you can calculate v, which is vx square plus vy square under the root, and you can calculate this angle here, which is tangent theta equal to vy divided by vx. And a similar idea can be used for the accelerations. So if you know the component of the acceleration, you can calculate the magnitude of the acceleration, which is ax square plus ay square, or a can be obtained using ax square plus ay square under the root. Now we can discuss now a projectile motion. So an important application of a two-dimensional kinematics theory is the problem of projectile motion. So now assume that the altitude change is small enough so that the acceleration due to gravity can be considered constant. So if you assume that the acceleration due to gravity is constant, and with this assumption, rectangular coordinates are useful for the trajectory analysis. So again, as you can see that we have this is the y coordinate, this is the x coordinate, and assume that somebody throw a stone or some object with some initial velocity, and which makes some angle theta with the horizontal. So this is the initial velocity of the object, and this initial velocity obviously can be split into two components. So one component is in the x direction, one component is in the y direction. So the x component is v naught cos theta, and the y component is v naught sine theta. Now we know that if we are close to the ground and the altitude is not very high, then we can assume that g is constant. Similarly, at any specific point, for example, at this point here, the total velocity is tangent to the path of the projectile. But again, we can split this into two components. One is vx, one is vy. Similarly, for this location here, the total velocity, which is v, is tangent to the path of the projectile. But again, we can split this into two components. One is x and one is y. Now again, you can see the difference between this location and this location here. That in this location the vy is upward, but in this location the vy is downward. Okay, now one important point that we can use all these equations for the projectile, because the acceleration is constant for the projectile. So as you can see that in x direction, uh, there is no acceleration because you just throw the object with some initial velocity, and then it depends on the initial velocity and the angle, and then it's just moving or following this path here. But then there is no acceleration in the x direction, so the ax is 0. So if ax is 0, so this means that the acceleration in the velocity in the x direction will remain constant. So this means that this vx naught should be equal to vx here. And in the y direction, we have acceleration, which is in this case you can see that it's in the downward direction. So it's which is minus g. So minus means it's just in the downward direction. So this is to show just the direction of the acceleration. Now if we use even these equations here, or if we integrate these equations, so we can integrate this equation in x direction and in y direction, and then we can calculate different equations. So if we use even these equations here for in the x direction, so if you want to calculate, because we know the initial velocity here, which is vx naught, and we know that in the x direction the acceleration is 0. So what we can calculate from here, that vx is equal to vx naught. So because the acceleration in x direction is 0, and similarly we can calculate, we can use this equation to calculate the range of the projectile. So we represent s by x here, and it depends on the initial position. For example, if it is 0, and plus v naught t. So v naught here is v naught x, and t. And again, if you have some initial displacement or initial range, you can also include that here. So x is equal to x naught plus v naught xt. So from here you can calculate and because the acceleration is 0, so in x direction, so we can just ignore this part here. Now in the y direction, it's a little bit complicated, because in the y direction we have acceleration which is minus g. But again, we can calculate the acceleration, the velocity in the y direction. So if we use this equation, the first equation, so we can say that vy should be equal to the initial velocity in the y direction, so vy naught, and then the a is g minus g, and then you have t. This will be the velocity in the along this projectile in the y direction. So for example, if you are interested to calculate this velocity or this velocity, you can use this equation here. So vy minus equal to vy naught minus gt. And similarly, you can use this equation to calculate the y displacement. So which you can say is y equal to. So this will become y naught and plus v naught y t. And if you use g here, so that will become minus half gt square. And so this will be the equation if you want to calculate, for example, this the distance here, the y distance at any instant of time of the projectiles. You can use this equation here, and these four equations will be available in the formula sheet in the exam.